Good morning, everyone. Good evening, good afternoon, wherever you are in the world. My name is Eric Jacobs. I'm going to be your presenter today for the OpenShift Administrators and Operations Master Course. I'm waiting for the stream to show me that it has started, so give me a moment here for my pause as I wait for things. All right. A little bit of housekeeping. We've got a lot of exciting master courses for you coming up. You can see them here listed. Today we have Operations 1. It is running again um, sometime in the future. And then we have Operations 2 coming up in, looks like a couple days on Wednesday. Uh, I am going to paste some links to some information while I tell you a little bit about myself. My name is Erik Jacobs. I am one of the technical marketing managers here on the cloud platforms team at Red Hat. I am focused on OpenShift operations type topics, as well as some administrative areas. Um, I also do a little bit of dabbling with artificial intelligence and machine learning in terms of technical marketing. I am a Ruby person. I also play with race cars. I don't do these two things together yet. Most of my race car stuff is Lua, if you can believe it. But I do both of those things, so I know a couple things here and there about development, so to speak. I have pasted a few links in the chat. The first one, Ops Master 1, that is a link to the presentation that I'm going through. I have also pasted a link, Ops Homework. That is a link to the content that I'm actually using as part of today's master course. And I have also pasted a link to this survey. Feel free to fill it out now and give me all positively amazing and awesome scores, or you can wait until the end and give me all positively amazing and awesome scores. What are we going to be talking about today? Today, we are going to be talking about operations topics. We're going to cover the automated installer. We're going to talk a little bit about how to scale an OpenShift 4 cluster. We're going to talk a little bit about separating cluster services from user workload. We're going to go through log aggregation and how to configure that and install it as well. I will do my best to try and pause and answer questions, but we do have a limited amount of time, so forgive me if I don't quite get to them. There's also quite a delay between when I say something and when you see it, so hopefully I will be able to return to whatever it is that you are asking about. All right, here we go. I totally just made a mistake. I'm going to talk a little bit about the OpenShift architecture very quickly. From a very, very high level functional perspective, the OpenShift architecture looks like this. Essentially, at its core, somewhat pun intended, we have either Red Hat Enterprise Linux or Red Hat Enterprise Linux Core OS as the underlying operating system that runs underneath the cluster. On top of that, we layer what you would know and love as traditional open source everyday Kubernetes. But then we add all of the value of OpenShift. This is our special sauce, our secret solution. All of it is, as you know, open source and freely available, but we just happen to package it and make it nicely, conveniently available to our customers. And this is where we have our automated operations, which is primarily what we're going to be talking about today. We have many of the cluster services that we provide as added value, our monitoring solution, logging, our registry and router, and so on and so forth. Again, we'll be talking about those today in great detail. We offer solutions like Service Mesh based on Istio, Serverless based on Knative, and lots of middleware and other runtimes, including a full ecosystem of ISV software. And then for developers, we have lots of different tools to help enable CI/CD, automated builds, and integrated development environment, and so on and so forth. What does a common implementation of OpenShift look like? Well, it looks a lot like this. We have a number of worker nodes and 3 masters that are distributed across some type of infrastructure consisting of compute, network, and storage. That could be physical servers in your data center. It could be the public cloud. It could be just about anywhere that Red Hat Enterprise Linux works and runs. Today's environment that I'm going to be interacting with and showing you is running on Amazon Web Services. And with that, we're going to switch over to the oven and pull something out that is already baked. And what I have here is an OpenShift cluster that is already set up and running. I've done most of the things that we were going to do as examples for today's lab exercises. And so what I'm going to do is log in via LDAP. I'm going to log in as fancy user 1, and I have the super secret password of OpenShift here. And when I log in as this particular user, what I see is that they have one namespace, one project available to them. It does have some stuff deployed into it, so we see some different bits and pieces of information here. And what we can do is go down over here and look at the logging tab. And we can log in again with that same user. Our logging solution is tied into the same credentials and RBAC system that everything else is. And what will happen here is that Kibana will come up, and we will see the logs for the application that we happen to have deployed. So really quickly right off the bat, this is kind of what you can get to very easily with OpenShift 4. Fully integrated, everything automated, mostly just pointing and clicking your way to success. The first thing we're going to look at here is the OpenShift installer. And if we click into here and go back to our slides, we'll talk a little bit about the two types of installation. The two types of installation you'll hear us refer to at Red Hat, full stack automation and pre-existing infrastructure. Full stack automation means exactly what it sounds like. We take care of everything. If you are deploying into a public cloud, we create the initial VPC in the case of Amazon, and then we put everything that you could possibly need into it. We configure DNS and load balancers and IP addresses and operating system instances and EC2 instances and all of the different things. And ultimately what you get is a full cluster where you pretty much just ran one command. On the other hand, we have pre-existing infrastructure. Certain customers have existing cloud accounts. They have existing network infrastructures that they have to lay OpenShift into. They can't necessarily delegate 100% of the responsibility to the installation. And so the pre-existing infrastructure install would probably be the choice for you. It still uses many of the same tools. You're just expected to have done many of the steps ahead of time. Fully automated installation. It's a simple text user interface. It takes your cloud credentials as inputs, creates all the cloud resources for you, which we talked about. And then it does the interesting thing that's special to the way that OpenShift is installed. It creates a bootstrap host. That bootstrap host then creates the cluster control plane. Then the control plane creates the nodes, and then we get rid of the bootstrap host. So we're not going to really dive into that today because it's basically just watching paint dry. We are going to talk a little bit about it more in detail with this eye chart. And essentially the big thing is that I can't highlight slides. That's annoying. The bootstrap machine is essentially creating the remote resources that are required for the control plane. You need an etcd cluster that's functional in order to have a control plane, but you don't have a control plane or an etcd cluster until you have a cluster. So it's a little bit of this inception-like situation where we need to control at least one host before we can actually have a functional control plane. And so we use a series of operators and predefined manifest files and moving Kubernetes components around between these hosts until we get to the point where the control plane is fully functional and self-sufficient. Again, how everything comes under management in the cluster, the masters are a little bit special. They basically are created and deployed and initially configured via this bootstrap process. Regular worker nodes, we use machine pools that correspond to machine sets. We're going to talk about those in a minute. And by default, we are doing this across multiple availability zones within our case for this lab today, within Amazon. We stripe the N machine sets that you create across all the different AZs. All right, so let's take a quick look at the actual installer itself. We're going to follow the instructions here that have us SSH into, there we go, make the text a little bigger. They have us SSH into this host here and export a little variable. And then we're going to list the assets. And if we look here, what we see is, I'm going to reset that real quick again. What you'll see is a number of state files from Terraform, which we happen to use under the covers in a non-user interfaceable kind of way. And then we have this auth folder. If we look in this auth folder, oops, what? Oh, sorry. If we look in the auth folder, permission denied. Hold on. try this again. All right, if we look in this auth folder, we see two files, kube admin password and kube config. Kube config, this is the initial sort of root user, super user for the Kubernetes cluster. This is a certificate-based authentication file that pretty much is the keys to the kingdom. So when you get done with the installation, you really don't want to share that with anyone. Kube admin password, we create a temporary cluster admin user that happens to have just a simple password. This is stored in a config map somewhere in the cluster. We're going to poke at that a little bit in operations 2. And then the other thing is if we look at the log file, tail-n5 OpenShift install.log, what we see is that at the end of the process, we were given the URL to the web console for the cluster, and we were given this kube admin password. So what did that installation process actually look like? If we run OpenShift install, what we see is that we have a couple of subcommands. One of them is to create a cluster, OpenShift install create cluster. And what we'll do is we'll be asked a series of questions about what we actually want to install. Hang on a second, I am looking here. Most of these questions are about authentication, which we're not going to address today. Come back on Wednesday for operations 2, and you can ask those questions. I'll be happy to answer them. When we run the installer, what we see is that we have a number of choices for the target infrastructure. In this case, AWS, Azure, GCP, or OpenStack. If I pick AWS, we'll be asked for an access key. This obviously is not going to work. We'll be asked for a secret key, whatever. We'll be asked for a region in which to install this. We'll be asked for a base domain, which it assumes that we have already delegated name server authority to in some way, shape, or form. A cluster name, a pull secret. This is used to access the OpenShift images that are housed in the Red Hat image registry. So I'm going to just type some garbage here. And then if I hit enter, what's probably going to happen is this is going to fail because I put in all types of garbage installation. And of course, a pull secret is JSON, so it wants actual JSON. So what I'm going to do is break out of this. But at the end of this process, after I answer these 4 or 5 text user interface questions, what we end up with is exactly what we showed before in that log file. We end up with a fully functional and installed cluster. It really is that easy when you're doing the full stack automation installation. If you're doing a pre-configured or a pre-existing infrastructure installation, you already have the infrastructure. So for the most part, you kind of already know what you're doing. Really, it's just a matter of making sure that you have the right infrastructure available that the OpenShift cluster expects, things like load balancers, subnets, and so on and so forth. The documentation for how to do that installation is very thorough, and it also includes example CloudFormation templates in the case of Amazon and templates for other clouds when you use those. But for the most part, the installation process, the base installation to get just a basic cluster is pretty easy. Now, this is my pre-baked cluster, so it has more nodes and infrastructure than the one we're going to be actually doing the exercises in today. If I go back to the cluster where we're actually doing the exercises today, 1, 2, 3, 4, 5, what we see is that all I have is masters and workers. I don't have any of those infra nodes, and there are 1, 2, 3 workers by default. Notice that they are, well, it's hard to see what region they're in, so we're going to come back to that later when we get to machine sets, which is actually right about now. Okay, cluster scaling. When we talk about cluster scaling, can you change the cluster name later? The answer to that is no. Can you do an automated install on non-Red Hat OpenStack? That is not supported at this time. It might work, but if it breaks, you get to keep the pieces. Okay, talking about cluster scaling. This is going to go into a conversation momentarily about operators. So there'll be a few more slides than the last time, but it's really not that many. how do we actually do cluster scaling in an OpenShift 4 environment? So the first thing to understand here is that this methodology necessarily requires that we have some type of cloud integration. So in the case today of Alibaba Cloud, we don't have a cloud provider integration there. You could install OpenShift 4 on Alibaba because we support Red Hat Enterprise Linux there, but we don't have a cloud provider integration quite yet. So scaling in this mechanism would not work. So in the context of EC2, which we're addressing today, we do have scaling, and it does work because we have this cloud provider. So what does this actually look like? We have this controller that we tell about machine sets. A machine set sounds exactly like it sounds. It is a set of machines, EC2 machines, that we want to have. Then there's a machine controller that makes sure that there are machine instances that exist that actually correspond to what's going on. The machine controller looks at the machine instances and makes sure that those things actually exist in the cloud. So if we have a machine that says there should be an EC2 instance, then there actually should be a real EC2 instance backing that machine. When that instance is created, because it is based on CoreOS, it will come up and follow an ignition process. This is somewhat incorrectly referred to as Bootstrap. It's a different type of Bootstrap, but bear with me. And ultimately what happens is you have an actual node object that gets linked to the machine object, and all of this stuff happens 100% automatically behind the scenes in the cluster. But what are operators? What do they actually do? How does any of this stuff work? Well, fortunately for you, operators are just regular pods. They are basically software that runs a control loop that ensures some desired state. And if we think back to a couple slides ago, the machine set operator, or really the cloud API operator, looks at machine set objects and ensures that the status of the cluster matches the desired end state. It ensures that the right machines exist based on the machine set that's defined. The machine controller ensures the right cloud instances exist based on the machines that exist, and so on and so forth. Operators make use of custom resource definitions to extend the Kubernetes API. This is a 100% upstream, totally nothing special about OpenShift kind of feature. CRDs have existed for a while. Operators are just pods. They make use of these CRDs. So in the case of a CRD, what does that actually look like? Well, you define a definition. I know that sounds silly and redundant, but it does. You create this custom resource definition that specifies the different fields and values and things. Basically, it specifies the validation for an object. In this case, we have a custom resource definition that is specifying an object called a car. And then on the right, we have an instance, a custom resource instance of a car, which happens to have a name of BMW with a manufacturing date and a particular engine code. And once you have defined these CRDs, you have thus extended the API to give you new objects that you can interact with natively. So in the case here below, you can see that you can do a OC get cars or a kubectl get cars, and you get a list of car objects in the current namespace. So again, when we think back to how we do cluster scaling, we have a number of CRDs for machine sets and machines and nodes and so on and so forth that ultimately are looked at by these operators, and that's how we do cluster scaling. The real magic of OpenShift 4 is operator lifecycle manager and the cluster version operator. So if an operator is just a pod that ensures the desired state, what that means is that that operator can control other software. It can manipulate the cluster, it can launch other pods, it can do other things. So the intelligence of what to do is baked into the operator. Well, what happens when there's new intelligence that's needed? I need a new operator. If there's new software that needs to be deployed by the operator, I need a new operator. And the way that we do this in OpenShift 4 is that we have this master operator called the cluster version operator, and it looks at the metadata for all the other operators that are supposed to be deployed. And if there's new metadata available when Red Hat releases an update, The cluster version operator says, hey, Mr. Administrator or Mrs. Administrator or other non-binary administrator, there is an update available. Would you like me to apply it? And when you click the button, what the cluster version operator does is it updates all of the other operators, and then those operators look at what they're supposed to be paying attention to, and if changes are needed, then they make those changes. And so this is the way that we do fully automated over-the-air updates with OpenShift 4, all using the power of operators. If we now go back to our little cluster here, sorry, I want to go to this one. Let's take a look at the machine sets that we have. So in this case, in this case, we have 3 machine sets defined. We have master course, US to East A, to A East, US East to B, and US East to C. These are the 3 machine sets that we have. And you can see that we have a desired state of 1 and a current state of 1, ready and available, and so forth. Because these are just standard Kubernetes objects, I can apply things to them, or I can do things to them using standard CLI commands. In this case, we have a OC scale command, which takes a desired replica count, but we can scale the machine set object, which happens to live, oh boy, sorry about that, copy paste errors. This lives in the OpenShift Machine API project, replicas 2, and we can scale this particular one, copy and paste. And it says, hey, this machine set was scaled. If we now look at the machine sets again, we see a desired state of 2 and a current state of 2, but only 1 are ready. Why is that? Well, because we're not done yet. If we look at the machine objects, what we see is we have this provisioning one right here. This is coming up. It is brand new. And so as this EC2 instance, which is backed by this machine object, comes up, eventually it will get ignition bootstrapped into the cluster, and it will become a node. If we take a look at this particular object, OC get machine -n OpenShift machine API, and paste, and we look at the YAML for it, we see a bunch of information about it. And buried in here somewhere is the AMI ID that we launched the machine from. And somewhere else is the actual EC2 instance ID, which I can never, there it is. Nope, that's the IAM instance profile. Where is the EC2 instance ID status? Here it is, instance ID. There you go. So this is the actual EC2 instance that is backing this machine object, which will ultimately become a node in the cluster. Let's recap real quick. What did we do? We ran one command to get an additional replica, an additional machine. And what happens? Eventually, we get a node. Don't mind this ugly URL here and the screen. I'm going to show you what this looks like from the web console. Really? I thought I accepted your certificate already. And for those folks who don't like the command line, we can come in here to compute and look at machine sets. And we see this machine set that we just scaled, 2 machines desired. We could have just as easily come in here and click the button and hit save and done the same thing. So no CLI required. We can simply scale to our heart's content, even from the user interface. We have some questions. Is the master node running replicas 2? No, masters are not replicated. They are individual machine instances. They are not backed by a machine set because they are special and unique snowflakes that need to be handled slightly differently. You asked a question, what does that mean? But you didn't ask what that was. If you can clarify your question, I will be happy to try to answer it. All right, infrastructure nodes. Let's talk about that real quick. What is an infrastructure node? So primarily, an infrastructure node is conceptually a thing. It's not actually a special type of thing. It really is a subscription agreement artifact having to do with the way Red Hat sells you software. An infrastructure node is just a regular node. There's nothing special about it other than the fact that it runs components that Red Hat considers to be infrastructure, which we don't ask you to pay for. So the control plane is free. You get 3 masters. You don't have to pay for the cores that run under the control plane. We don't charge you for the control plane. Worker nodes, where user application runs, that's what you pay for. How many cores do you want to cover? That's what you pay for. Infrastructure nodes are this special thing where they're just regular nodes, but you're only going to run certain components on them. And those certain components are the built-in container registry, the router, which is used for ingress, the cluster monitoring solution, the cluster logging solution, and a couple other various components. These are things that Red Hat considers infrastructure that we don't charge you for. Some customers are totally happy with running these components alongside user workload. They couldn't care less where they run. It's just stuff that's running in the cluster. They don't care to segregate it. It's totally fine. However, other customers want to segregate these things for whatever reason. They have extra security, regulatory compliance issues, what have you. Some people just want to run these things separately, and that's totally okay. You can do that, and we don't charge you extra for it as long as you sort of do this one thing, which is create them as infranodes. So what does it look like to actually create the infranodes? Well, it really doesn't look all that particularly interesting. You're just creating machine sets that happen to have labels. And if I find that lab, here we go, infrastructure nodes and operators. If we scroll down in here, we've already talked about machine sets. Machine sets just define some machines that you want to exist. They have various bits of metadata on them. There are selectors that tell the operator which machines are associated with which machine set. There's additional template metadata that defines other things, and so on and so forth. Ultimately, when you want to define a machine set, you have to make sure that you create all the little templatey things correctly. In the case of this lab exercise, we have this sort of pre-existing bash scriptlet and JSON that will take care of everything for you. If you look at the actual OpenShift documentation in the section for, I think it's in the installation section. Where is it? You know what? Let's do this. Infrastructure node. Creating infrastructure machine sets. So in the OpenShift documentation is a whole section that explicitly tells you everything I just told you with examples and more detail about how to do it yourself. But ultimately, all we're really doing is we're going to run a command that's going to define some YAML objects, which are machine sets. And then what we see is we have a machine set called infra. Buried in this machine set definition is a label, which is just a key value pair, a label for a node. And if we go over to the oven and we take the cluster out of the oven here, what we see is at the end of that process, after everything comes up, we have some nodes that have the special name of infra. That's it. They have a label called infra. That makes them an infra node, as long as they're not running end user application. From an end user agreement perspective with Red Hat, you are only allowed to run the components that we deem as infrastructure on an infrastructure node. If you do something else, you should be paying for the cores that are covering those hosts. If we now have infrastructure nodes and we want to actually take care of the isolation of the components, we have to understand a little bit how each operator, how each component handles scheduling and where it's going to go. In the case of the router, we have an operator that manages the router. Where did that just go? Here we go. If we look at the OpenShift ingress operator pod, this is the operator, just a pod, that is going to manage the router. If we look at the pods in the ingress project, we see that we have two. We have a router and we have another router. This is the HA that we provide out of the box with the installer. We have two HA proxy router instances, which are providing ingress for traffic into the cluster. And when we install the cluster, we create an EC2 load balancer that balances traffic, across these two routers. And so if one of them were to die or have a problem, the EC2 load balancer that sits in front of these two things just picks up the traffic and sends it to the other one. So out of the box, we provide HA. The router is immensely configurable and scalable. You can shard it. You do custom certificates. You can do all kinds of crazy stuff. But out of the box, you get two routers with a default SSL certificate and some wildcard DNS. So how do we tell the router to go to a specific host? Well, the router uses a CRD called ingresses, and there is an ingresses that is called cluster. And that ingress has a domain definition and a status, right? So this defines the default routing configuration. If you wanted to change where the router goes, there we go. We can change the ingress controller configuration to specify a node selector. What does a node selector do? A node selector tells the Kubernetes schedule to select a node whose labels match. In this case, we are selecting for a node whose label is Kubernetes IO infra. Right, so this is selecting for an infra node. And as soon as we make this change to this operator configuration via the CRD of an ingress controller, the operator immediately notices that it's been changed and it fixes the problem. It reconciles the difference in state, and what it does is it redeploys the routers with the new selector. And so if we ultimately look at where these routers are living, one of them lives on 130, 143. The other one lives on 130, 138. And if we look at the nodes, we see that 130, 143 is an infra node, and 131, 38 is an infra node. Whereas in the other cluster that is not what I would call the oven, OpenShift ingress, OC get pod -n OpenShift ingress -o wide, we see that we have 150-30 and 173-157. At this point, our infrastructure nodes are up in the other cluster. Notice that the router is not on the infrastructure nodes. It's still on 150-30, which is one of the regular worker nodes. So until we make this change, the router's not going to move. Let's look at how fast that change actually happens. If we scroll up, I saw there are a couple of questions. I will get to them in a moment, I promise. Where is that? Moving the router. Okay. When we make this change and we apply it, OC apply, here is the pod, and then I will apply, and then I will look at the pods again. And what we see right now is container creating, right? I applied that change. The operator knew that there was a change, knew that it needed to do something. So what did it do? It already scheduled a new router. So that took like not even a second, basically. And ultimately, what's going to happen is we'll see that the routers end up on the new hosts. How did we do this? How did we reconfigure our infrastructure? We applied 6 lines of YAML that are documented. Could we have done this in the OpenShift user interface? Yeah, we think we still would have needed to use YAML, but hey, it's really not that hard. There's a note here about the session may time out. This lab guide I'm using is actually running inside the cluster, so it's backed by the router. At some point, the router that I'm going through, and you can see it just happened, we got this closed message. At some point, the router that I was going through got terminated because another one had been placed in the correct spot. So at this point, I just need to refresh my connection. Now, it's going to be pretty uncommon for you to kill all of your routers at once. Oops. Just waiting for this to come back up. So this is kind of an unlikely like to do other than on day 2 operation kind of thing, but just understand that that's a thing. All right, let's look at a couple of the other things really quickly. Nope, actually I'm going to go to your questions. Machine set for master. There is no machine set for the masters. The masters are not backed by a machine set. If we do a OC get machine -a, sorry, I'll make this a little bigger because my font is huge. If we do a OC get machine, we see that there are machine objects for the master, but you see how they have this like hyphen after them? They are individually created during the bootstrap process. If I delete one of them, I have done a very bad thing, right? Because there's nothing managing keeping master instances created. This is very important to understand that today, masters are not backed by a machine set. Only regular standard workers are backed by a machine set. Also, one thing to note, this cluster only has 3 machine sets by default, 2A, 2B, 2C. Why is that? Because US East 2 only has A, B, and C. It may have more depending on when you created your AWS account, which is super weird, but whatever. Is there a complete list of what's allowed, what to run on InfraNodes? Yes, there is. It is in the documentation. There's also a lovely fancy PDF that has pictures in addition to the words. I like it because I made it, or at least I made part of it. That also tells you specifically what infrastructure is and what is not. Okay, we did the router. We are going to do the registry. The registry is similar but slightly different. There is a config map called image registry. There's a config of image registry that has a name. It has a bunch of stuff that it's supposed to do. If you run this patch command, which adds a node selector, it patches the image registry. And then if you look at the pods, you will see that eventually they will get moved around. You can see already this one's not ready, but it's already running, so I wasn't fast enough to catch it being created. If I do this again, what we'll see is that there's only one registry now, and that is the new one that's running on the correct nodes. Can I share the lab link again? Yes, I'm happy to share all the links again. First link is the slides. Second link is the lab content. And then third link is the survey where you're going to give me awesome ratings. Will you cover adding storage? Storage is covered in the next master course. And can you share the lab link? I did. Okay, cool. Monitoring, same kind of thing. The interesting thing about monitoring is that by default, we don't configure anything. The config map for what to specially do with monitoring actually doesn't even exist out of the box. So it's using all defaults because you haven't asked it to do something special. What we can do is create a configuration for it that asks it to do something special. And then what we'll see is that the pods are all going to get moved around. Monitoring is pretty complex of a solution. There's node exporters, there's alert manager, there's Grafana, there's Prometheus. So you can see it's like there's terminating happening and creating happening and all this other stuff. And so eventually what you end up with is all of the pods are running on the new host, right? So this one takes a little bit longer, but again, we changed one file and basically just added a bunch of like the same thing over and over. And a whole bunch of software got redeployed. So this is like illustrative of the power of operators in general, right? did monitoring. Okay, the next thing is cluster logging, which we're actually going to have to install first because it's not there out of the box. It's available, it's supported, it's included. We just don't install it by default because not everybody wants to use our flavor of log aggregation. So we will return to the slides to talk about cluster logging. What is our log solution? Well, it is multi-pod log corroboration. We provide a solution that makes it easy to figure out when you have lots of application components deployed, exactly what's going on, right? So if you had 10 pods in a namespace and you didn't have something that pulled all those logs together, it would be really hard to look at all 10 pods at the same time. We use a solution of Elasticsearch, FluentD, and Kibana to aggregate and display and allow for searching our logs, or the logs in the cluster. It is secure and multi-tenant in the sense that it is backed by the RBAC of the cluster. So you can only see logs for things that you normally would be able to see. If I can't see a pod in a project, I can't see its logs. Somebody needs to give me access to see the logs in order to see the logs. This does not replace traditional SIEM solutions, right? It is not a guaranteed, durable, catch every log message, keep it forever type of thing. There are many solutions on the market that can do those things. This is not that. So as long as you go into it with the expectation that you're not gonna replace your CM solution with the OpenShift logging, you'll be pretty happy. The people that have tried to replace Splunk or some complicated log aggregation system using just the EFK that we provide, they're generally unhappy because it doesn't perform at that scale, at that level. It's not its job. How does the logging solution work? Well, you might be not surprised to know that it uses operators. There's actually two operators in play. There's the cluster logging operator, which deploys Kibana and all the FluentD, and the curator, which erases old log messages and stuff like that. And then there's the Elasticsearch operator, which deploys and manages the Elasticsearch cluster. The dotted line is there to sort of illustrate that when you configure cluster logging, you don't say anything specific about Elasticsearch. You only deploy a cluster logging CR config. The cluster logging operator takes care of telling Elasticsearch what it wants of Elasticsearch, and then the Elasticsearch operator makes that happen. You will see, if you dive into all of the cluster operators in more detail, you'll see that a lot of them operate in this kind of way. There's one that basically sets up what the other one should be doing. From a data flow perspective, what happens is we have FluentD running on the node, or all the nodes. FluentD is configured to pull the log messages from the container runtime. It captures all of those, and then it sends them securely directly into the Elasticsearch cluster. When users go to look at the logs, they access the logs through the Kibana interface. We technically do not support direct access to the Elasticsearch. So the APIs are there, they're available, but if you're using them directly, you're sort of doing like unsupported territory type stuff. Part of the benefit to the way that we use Kibana is Kibana and its OAuth proxy are enforcing the RBAC on the information that is contained within Elasticsearch. To go a little bit deeper into kind of how this works, FluentD is actually looking at a combination of the operating system disk area where the container runtime is directing the standard out and standard error messages from containers. And it's also looking at journal D because it's pulling in information about kubelet and the node operating system as well. So a cluster administrator gets access to log information about the kubelet and everything else that's running directly on the node. And non-cluster administrators just have access to their normal container stuff. All right, what does the log aggregation solution look like in practice? I will go to the installation documentation. We're going to go now through, oops, that's the wrong exercise. We want OpenShift log aggregation. And what this one is going to do is it's actually going to take us through using the OpenShift web console to install and deploy operators. The one thing that it asks us to do from the command line is to create a project, OpenShift logging, to hold the logging solution. This is where all of the logging stuff is going to go, all the pods for Kibana and everything. They're going to land in this project. After that, it says go to the console to install the Elasticsearch and the cluster logging operators. When we come over here to the web console and we click into operators, we have the operator hub. The operator hub is a curated, it's a curated content repository of operators that are certified by Red Hat, as well as non-certified community operators. In this case, if we sort of look through here, we click into databases real quick, we see things like Crunchy, PostgreSQL. This is an enterprise database Postgres solution designed to run on Kubernetes. They provide an operator. What does the operator do? It knows how to install Postgres instances. It knows how to upgrade them. It knows how to back them up, and so on and so forth. So what we're specifically going to look for is the cluster logging operator. Oops, sorry. The first step is to install the Elastic operator. I always get this backwards. So we click on Elastic, we click on install. We're going to install it everywhere, so we're going to make it available in all the places. The particular instructions for this lab say use update channel 4.2. Click subscribe. Notice that there's all these different update channels that correspond to different OpenShift versions, right? That's a common strategy for the way operators are installed and managed. The next step in the instructions, it said, was to install the actual cluster logging operator. It says to choose a specific namespace on the cluster. In this case, we are going to choose the OpenShift logging namespace. It also says to choose 4.2 as the update channel as well. I'm actually going to do one slightly different thing here because I noticed what might be a bug, but bear with me. Cluster logging, install 4.2, OpenShift logging, automatic approval strategy. What this means is that if upgrades or updates appear, that we will automatically approve them. We don't have to actually click a button to say go ahead and do an update. And what we see here is the Elasticsearch operator has been installed in our logging project, and the OpenShift logging operator is being installed. If you remember, we talked about this ad nauseum. What are operators? They are just pods. What do we see here? Well, we see the cluster logging operator pod being deployed into the OpenShift logging project. We don't see an Elastic logging pod here because it actually lives somewhere else. It doesn't need to live in this particular namespace because it looks at everything. Okay. We did the operator installation. Now it says create the logging custom resource. In the OpenShift console, go to administration, CRDs, and so on and so forth. If we go to administration, custom resource definitions, what we see here now is cluster logging, right? This didn't exist previous to installing the operator. As a part of installing the operator, we created the cluster logging CRD. When we click into the CRD and we click at the instances, I need to refresh my browser. We see this button to create cluster logging. This is to create an instance of the cluster logging CRD type object. The lab guide has a copy pasta example of how we're going to define our cluster logging object. So here's my copy pasta. The storage that we're using for Elasticsearch is actually GP2. 10 gigs is more than enough. If we look at this really quick, what are we doing? Well, we're specifying how do we want Elasticsearch to be deployed? How do we want Kibana to be deployed? Do we have a node selector that tells it to go somewhere specific? What about the curator? What about fluentd, right? The fluentd logs node selector is actually ignored because fluentd needs to run everywhere, always, otherwise it wouldn't work. That's a bug in our lab guide. When I create this cluster logging instance, if I go back to the pod list, why is this not ready yet? I have made some kind of error in the way that I did this. So what I will do is switch to my baked cake cluster, which already has pods. OpenShift. Oops, sorry, logged in as the wrong user. Okay, so if we go to workloads, pods, OpenShift logging, what we see is that ultimately we have all of the Elasticsearch pods, we have all the Fluentd instances, we have the Kibana instance, everything came up where it was supposed to. And if we look at Kibana, which we actually was the very first thing that we did when we got started today, this is where we're logged in as a particular user, fancy user, who's looking at logs from the pods. So this is kind of how all the operator infranode logging stuff all comes together. Look at your questions really quickly. Fluentd are doing the same as FileBeat. I'm sorry that I do not know what FileBeat is, so I cannot answer. Do multi-line logs display in Kibana? I believe so. I mean, this is basically just pulling whatever gets spit out. So if it's multiple lines in terms of how standard out captures it, you know, it's gonna it's gonna look like a single message. I think what you're asking about is more kind of related to like JSON logging and some structured log data, um, maybe. And if that's what you're asking, like we don't support that super awesomely right now. We basically just capture um, the message that gets spit out of the container, which is here in this message block. And as you can see, it's just one line. In this case, it's one line. Each message that gets written out appears as a line, I should say. So if you're talking about like a stack trace, which is 30 lines, because that stack trace message shows up as standard out, spitting out 30 individual lines, that would show up as 30 entries basically um, in this. Actually, this is a good example of what you're describing. If I add the message field over here, you'll see this is a stack trace out of a Java application that blew up, and the stack trace came in as a bunch of individual lines. We're in, okay, please, the guide to deploy Kibana. That's just in the OpenShift documentation in the logging section. Can I get operators if my environment is not connected to the internet? Yes, we have a whole section of the product documentation that tells you how you can mirror the operator hub and pull down the images and store them in your own private registry. So that's fully supported, no problem there. If you have the container Docker images locally, um, oh, that's like an answer to Chris's question. Yeah, I mean, not locally in the sense of like you have to put them on every host, but locally in the sense of you have some internal image registry that is accessible to your cluster that holds the operator images. And again, that's fully documented, fully supported. I will paste the links to the things again. Here are the slides. Here is the lab content that we went through that includes instructions for how you can do it in your own cluster. And lastly, one more time, here is today's survey. I have been joking about, make sure you fill out all awesome. We do appreciate the feedback. We want to know how we can make these courses better, additional things you might want to see. Actual feedback from me, I do take it into consideration. I don't just circular file it. We very much appreciate your time with us today. I will pause in case there are any more questions because there is quite a significant delay. But with that, we have reached the end of the content for today. So again, thanks so much for your participation. I'll give it a few more minutes and then we will end today's session. So the question that came in is, what about 311? But I need more context. Sorry. Alrighty, well, I didn't get clarification. Oh, is there a link to this video? I think, well, if you have the link to watch it, you have the link to it. YouTube doesn't change. Um, the link you're watching is the link to the video. How do you do the same install on 311? So 311 has a completely different installation mechanism. So you'd have to look at the documentation for that one. It's totally different. Thanks so much. Deploy Kibana. Does it support the same installation configuration? No, 311 is totally different. Yeah. Is there documentation for how to scale the master nodes or how to separate the etcd service? No, we don't document those things because we don't support them. Red Hat has taken the stance that 3 masters with etcd living on the masters is the only supported way, and that is the mechanism to stay supported for up to the maximum scale of cluster size that we support. I used the word support like 5 times in that sentence. Yeah, so basically we have you install the control plane with the etcd co-resident. It's the only way we support OpenShift 4, and that's basically it. So eventually we may have single master or single node cluster, really one host. We're not there yet. OpenShift 4.5 introduced a compact cluster, which is just 3 nodes, so only masters. But there's no roadmap right now for separating etcd in OpenShift 4. Yes, OpenShift 3.11 is for the OGs. The second part of your question about in case you need more than 3 masters, again, like Red Hat has decided that you will never need more than 3 masters. And so we just simply don't support it right now. Sort of an odd answer perhaps, but that's the way we've done all our engineering and QE and support validation for the scale that we are claiming that you can do. All right, everyone. Thanks so much again for your participation and attendance. We really, really do appreciate it. Hopefully you have registered for Master Course 2, which will take place at the same time, 12 p.m. Eastern, on Wednesday, July 22nd. And if you haven't, please go sign up for that. I would love to get to talk to you again then. All right. Have a great evening, morning, nighttime, afternoon, whatever time it is for you. Enjoy the rest of your waking hours, I guess, and we will see you again soon. Cheers.